Okay, now time. So now we want to start first session of afternoon. The first speaker is Professor Liang Kong from SUSTech Institute, Shenzhen Institute of Quantum Science and Engineering. The title of his talk is The Category of 2D Rational CFTs. Please start.
Yeah, thank you. Thank you for the invitation and the introduction. So today I'm gonna talk about the category of 2D rational CFTs. The main goal of this talk are to briefly outline the development of the mathematical theory of rational CFT, okay, based on the representation theory of vertex operator algebra, which is also called the VOA. Well, the second goal is to show how the language is refined and simplified in this process, and show that eventually it leads us to the study of category 2D rational CFTs, which is impossible without the language simplification. Okay, so that means to study the category of all these CFTs in the early stage of the development of CFT, this is impossible because the language you attack the CFT is too complex. Okay, so only after a lot of simplifications, the study of the category of these CFTs become possible. Okay, the story becomes really long, but I will briefly, before I jump to the mathematical theory, let me mention briefly outline the history before the mathematician, or almost before the mathematician started the mathematical theory. It has a very long history. I think the first, the CFT was originated from the study of critical phenomena in physics and the strong interactions in physics, okay? But in the early history of this development, mathematicians also made a contribution. For example, the appearance of Virasoro algebra was first discovered by mathematicians instead of physics, but now it does not have the physics name. Okay, it's called Virasoro algebra. Okay, the second important development called the OPE, which means operator product expansion, is proposed by a physicist, okay, Polyakov and Kadanoff and Wilson. Then the conformal bootstrap approach appeared proposed by Polyakov mainly, also Farah and all his collaborators in the Western world. The conformal bootstrap is a new way to understand the well. So I have to say something about the CFT. I made the abbreviation of CFT. It means conformal field theory. Sorry, I should really mention that. Conformal field theory is some kind of quantum field theory. In my talk, the conformal field theory means two-dimensional conformal field theory. So it's a quantum field theory with a conformal symmetry. Okay, so because the conformal symmetry in 2 dimensions is really big, really large. So it made the conformal bootstrap approach available because symmetry is too big. It just significantly restrict the content of the field theory. Okay. After that, I think another significant progress is notice the appearance of Virasoro algebra in the conformal field theory. That's around 1972. Later on, Polyakov generalized formalized the conformal bootstrap in terms of so-called operator algebra, which is beyond just conformal symmetry, and he introduced the structure constant. That's the very important. And the next, I think, fundamental progress is the representation theory of Virasoro algebra developed in 70s. Okay, especially the last one. This last one was fundamental progress and paved the way for the next important progress called the chiral algebra and minimum model construction conformal field theory made by Belevin, Polyakov, Zamolodchikov, okay, in 1984. Very important progress. I think a lot of people will, when people talk about the modern development of conformal field theory, they will always say it started in 1984. Okay, so after 1984, there is a lot of development on conformal field theory. There are just a ton of them. I'm not going to go through this, but this flood of development was almost stopped by the famous work by Morris Seiberg, in which they introduced the chiral vertex operator and the modular tensor category. This work almost killed the subject in physics. Yeah, well, almost killed it, or probably killed it almost. Yeah, in a way that after 1989, very few physics work in this direction appeared after 1989. People believe that the subject was already quite well understood. So after 1989, you can see the fundamental progress are all made in the math, on the math side. Okay, in the recent year, this direction become more popular is because its application in condensed matter physics, especially in the study of topological phase matter. So that's one of the motivations why I start to review this, because this topic become more and more important to physics, and the development of mathematics, mathematical theory is not only making the theory which is known to physicists much more rigorous, not only because that. I think more important is that as the mathematicians develop the mathematical theory, they also polish the language. Not only make it rigorous, they make it simpler. Okay, the refinement of the language play a very important role to the later development, which is almost impossible without this language simplification. Okay. However, even for the math part, the story is still very complicated. There are essentially four approaches towards the 2D rational CFT. One of them is the conformal net from operator algebra. Okay, another is called the FRS formalism based on the 3D TQFT. FRS simply are the initial of the three people, Fuchs, Runkel, Schweiger. Their approach is mainly from TQFT. They use TQFT technique to construct the structure constant of the modular invariant correlation function in the 2D CFT. Another approach is called chiral algebra and chiral homology, mainly led by the Russian school. But this approach were limited to the chiral case. But conformal field theory include the non-chiral part. So, but this side story also very important. Okay, I think is the key development in this direction is Bayes and Drinfield's preprint in 90s. Later on, it was published in a book. I think in 2004. Okay, it's also very important development. However, I'm not going to cover all the first three. Only thing I'm going to cover is the vertex algebra approach. Okay, so I will restrict it to the first, the last one. Okay. All right, so let me briefly explain how the vertex operator algebra, which was also
excuse me.
Yes.
Before going to your topic 4, but let me ask about the topic 2. What is 3D TQFT exactly?
Oh, 3D TQFT, yeah, it's a three-dimensional topological field.
Yeah, I know, but is it a kind of Chern-Simon theory or something different?
What theory? I didn't hear.
Chern-Simon theory. I know the example.
Oh yeah. I to be more precise, I should say Rastikin-Turayev TQFT.
I see. Okay. Thank you.
Yeah, it is Chern-Simon theory.
Yeah. Okay. Okay.
Thank you. Yeah.
Okay.
Yeah. Any other questions? All right. If not, let me continue. So the birth of VOA have a very independent story. It's a start from the story start from a very interesting one. It starts from 1978. John Mackay observed that one of this number appeared in a power series expansion of a J function. Perhaps I heard the story. He went to attend a course in a number theory, maybe, or and this J function is a modular function, play a very important role in number theory. And this coefficient is pretty big one. And he made a comment that this number is another number plus 1. Okay, and this another number is the dimension of the smallest irreducible representation of the monster group. Okay, I think people were joking about his observation, saying that, well, we study mathematics. Occasionally, there two number in a different field of mathematics become closer. There's nothing surprise about it, right? But it turned out that this observation is not so trivial, because people immediately notice that the next number, okay, in the power series expansion, also have some relation to the representation, the dimension of the representation of monster group. Okay, it is 1 plus this number. This number is same as this number. But the next number is the second smallest irreducible representation of monster group. Okay, so then the observation become non-trivial, and we can imagine that if this is true, the people immediately formulated the so-called monstrous moonshine conjecture by Conway and Norton. Okay, so it simply says that there is an infinite dimensional graded vector space. All right, and each VK, the homogeneous space, is a finite dimensional representation of monster group. Okay, the more precise conjecture is about the so-called Thomson-McKay series. Okay, and how it what kind of property it satisfies. But I'm not going to read this because it's not so relevant to our story. Okay. So the next important thing is that although we mentioned that it's already mentioned here, it's a representation of monster group, but actually the monster group is not explicitly constructed until 1982. Okay, Bob Grice, the Robert Grice construct the so-called give the explicit construction of monster group. Okay, so I think after this construction, it become more interesting to study so-called monster moonshine conjecture. All right, this conjecture was had a breakthrough almost just 2 years later, or 1 year later. Okay, the construction of monster moonshine module was conjectured in the previous slides, right? But now it was explicitly constructed by Franco, Lapolsky, and Merman. Okay, they did it. They announced it in 1983, just 1 year later. So pretty amazing. Okay, and I think the paper was officially published in 1984. It's in the same year. In the same year, Balavin, Polyakov, Zamolodkov discovered their conformal field theory, discovered their minimal model construction of a 2D conformal field theory. Okay, so because it's published in the same year, and the relation of 2D conformal field theory was so noticed by audience attending their talks. Okay, because their physicists are sitting in the audience, a pretty interesting one. So the relation was immediately noticed. Okay, so but I want to point out that they constructed a monster moonshine using a so-called vertex operator, which already appeared in the work of 70s. Okay, people already noted there's some kind of interesting constructions called a vertex operator from the study of affine algebra in 70s. Okay, but so in this monster moonshine construction is full of this kind of vertex operators. Okay, but they didn't introduce the notion of vertex algebra or vertex operator algebra until a couple years later, by a deep observation by Borges. Borges tried to read their paper, read Franco, Merman, Lapolsky's paper very seriously, and he discovered an algebra structure out of this construction of FLM. Okay, Franco, Lapolsky, Merman. And I cut from the original paper, this part involved the so-called vertex algebra. And you can see from the fifth axiom. The fifth axiom is a very important one. It's called the Jacobian identity, okay? This one. And you can look at this formula. It's very, very long, okay? Very complicated. So at that point, to be honest, any mathematician who are familiar with the notion of algebra in mathematics won't be able to say this kind of a mathematical structure is some kind of algebra. It's really hard to, it's not algebra in any classical sense. Okay, and even if this way of formulating this algebra structure does not make it looks obvious that it has any connection to physics either. Okay, because physics have the notion of field, but this expression, it does not show you where the field of quantum field looks like. It doesn't see any connections of this. Okay, so yeah, that's also, but this is very important. Okay, almost immediate after that, Franco, Lapolsky, Merman was polishing. They refined Borges' discovery. and they wrote a very important book, which play a almost very crucial role in the development of vertex over algebra in the early, especially in the early stage. Okay, very important book in which they introduced a new version of Jacobian identity. We should look at this. Look at this. Okay, you can take a look, and now it looks different now, right? Compare with the previous one. Okay, compare with the previous one. There's no variable z, but now you have a variable z, which make the expression looks like a quantum field. So this is very important progress. You see, from mathematical part, very single small step is a big step to mathematician. Okay, to clarify all these things is very important. That the precision, okay, the rigorousness paved the way for the further development. Okay, so that's 1988. Okay, after that, okay, after many years of progress, many years of simplifications, I used the Dong's lemma and the Heisen-Lee's local system. Eventually, a few books appeared, and the definition of the vertex operator algebra is simplified. Now you look at the definition; it's only in the one page. I'm not going to show you. I'm not going to read the details, but just give you some idea. Okay. Now the definition can be written in the one page. That's already amazing because well, just like the real number, you know, if you write down the XML real number, that's also will be really long. Okay. And in some way, vertex algebra can also be viewed as a quantum field theory. Well, it is quantum field theory, but I mean the field theory in a mathematical sense. It's a quantum version of classical field theory in some sense. Okay, yeah, that's a VOA. You can see how it was developed. So this tells you that the foundation of VOA was established, and what's the next thing to do? What's the next thing to do is that obviously you need to develop the repetition theory. Okay, develop what the algebra theory of the vertex algebra is, especially the repetitions, right? But there are two ways to develop a vertex algebra. Besides algebra theory, there is a geometric theory. So from here, the reason I separated it because I want to give you two separated stories. One is a geometric theory, another is algebra theory. Okay, so let's start from the algebra theory first. These two theories developed at the same time. Okay, so I have to split them, otherwise the logic will become a little confusing. You know, so I'll give you two routes of development. Let's start from the algebra theory. So the first important development after the mathematical definition of VOA was established, I think the next important, well, there's the obvious thing one can do is to introduce the notion of modules. Okay, but beside the modules, I think, but you know, the notion of modules is not that hard. It's sort of pretty convenient. You can just do it. But there is one notion which is highly non-trivial. It's not the classical, and you won't see this in the classical notion, even though it has a classical counterpart, but it's very new. It's different. It's called a chiral vertex operator. First introduced by physicists, not in a very rigorous way, but eventually become a so-called intertwining operator. Okay, so the definition of intertwining operator was written down in a book by Franco Huang and Lapolsky. The definition looks like this, and this condition also called the Jacobian identity is very similar to this one. It's very similar to this one. Okay, you can see the Jacobian identity here. There looks very similar, but to write it down explicitly in this way play a fundamental role in the history of the development of conformal field theory. So this chiral vertex operator or intertwining operator play a very important role in the later development of the subject. So that's why I want to highlight it. Oh, by the way, why it's called intertwining operator? Because classically it is called intertwiner. For example, from the group theory, from the representation of group, you can have a representation of a group. You have another representation of a group. You tensor them together. In the group case, it is still a group representation, and you can map to the third group, third representation of group. That's called intertwiner. Okay, but in this case, it is in the same spirit as intertwiner. That's why it's called an intertwining operator. But it is highly different. Okay, look at this axiom. Okay, it's very different. It had a lot of new things, so it's highly non-trivial. Okay, that's what I want to tell you. So the second important progress is Zhu's thesis, okay, in which he did two things. The first thing is that he introduced the so-called Zhu's algebra, which is a associated algebra defined on a quotient space. And I'm not going to give you some detail of this, okay? So you start from a VOA, you define a subspace OV in some way, and you quotient it, you get a quotient space. On this quotient space, you can define an algebra structure, which is associative. What is amazing is that this Zhu's algebra controls the representation theory. So that's a very fundamental progress, okay? The second progress he made is that he proved the so-called modularity of partition functions of modules over a rational VOA. By that we mean, what is the partition function? It just means you do a trace, okay, a Q trace, so-called. Q is a complex number, and L0 is the grading. Okay, is the grading of the module. Okay, C is so-called the central chart. Yeah, but anyway, it's almost like a trace of some. It's also called a graded dimension, by mathematicians. Okay, and it turned out that all these things, all these partitions functions form a representation of a span. Okay, you can span the vector space by changing the irreducible representation, right? They span the representation of the SL2Z. Okay, modular group. This is a very, very fundamental progress in the study of conformal field theory. Moreover, he had not only showed that, he showed that you can do a much more general trace, okay? By inserting, previously it's just a Q, right? But now you insert some kind of some Y, which is a vertex operator. Okay, you can also prove the modularity of this kind of a generalized correlation function. But very importantly, these Y are restricted to the module actions. There is no intertwining operator. This is very important because if you have an intertwining operator, you can almost prove the representation theory of representation, the category representation of V modules, representation over V, form a module sensor category. That's one of the fundamental goal guiding the development of on the mathematical side. That conjecture actually was already made in Morris Seiberg's 1989 paper, which ended the development in physics, right? So that's a very important conjecture guide the math development. However, after Zhu's thesis, you can still not prove this conjecture because Zhu's proof does not contain the intertwining operator. Okay, so the study of intertwining operator is also very important missing piece. Okay, after Zhu's thesis, because I said that the Zhu's algebra control the representation theory, so Zhu's thesis immediately tell you how to go from there to really study the representation theory. Yes, there are quite a few work on this. For the time reason, I'm not going to go through detail, but you can see for the concrete example, people using Zhu's algebra, they can really study the representation of concrete vertex algebra, okay? Especially from affine, especially from the affine-Lie algebra and the Virasoro algebra, okay, called minimum model. Okay, so the next important thing I think is the tensor category theory of the module over rational VOA, which really depends on the intertwining operator. Recall that we have a so-called intertwining operator like this. And but the problem is that this tensor product is the tensor product over a complex number. After you do this, 2 module over V, after you do the tensor product, it's not a module over V anymore. So that makes the problem really non-trivial. So so E. Zhihua and Lepofsky eventually developed this tensor product theory, okay, which usually denote the box tensor product. What they do is that they start with the dual vector space, which is really big, right? Because everything is infinite dimensional. This is a dual vector space, really, really big. What they did is they find a relatively small subspace of this. From there, you can define the tensor product. Okay, that's the basic idea. All right, there are many important algebra study of VOAs. But unfortunately, all these work are not so directly related to what I'm going to talk about, so I won't expand the discussion here. Okay. Well, next important thing is the Huang's proof of a Linder formula and the modular tensor category. As we already mentioned, that prove that rational vertex orbital algebra give a modular tensor category as the module as the category of module over this vertex orbital algebra. Play a fundamental role in the development of conformal field theory, mathematical theory of conformal field theory, or mathematical theory of VOA. So Huang's theorem have been long expected, but eventually were proved. Eventually proved almost 10 years after Joule's theory. Okay, or more than 10 years, maybe 15 years after Joule's theorem. Okay, so very interesting one. So what the basic say is that if a V, what? Did someone ask a question?
No, maybe please, you know.
I'm sorry. Can I continue?
Yes, continue.
Okay. So Huang's theorem basically says that a VOA satisfies some natural conditions, and then it's the module category is a module tensor category. This is a very, very important theorem. Another theorem that plays some role to the later development is say that if you have a rational VOA, a VOA extension of V is equivalent to the community algebra in the tensor category. This theorem is very important, even though it's quite simple. It can be simply derived from Huang's big theorem. This is a much bigger theorem. From there, you can easily derive this. But this result play a fundamental role. Okay, it tells you that VOA which is such a complicated subject, can be simplified in a categorical language. Okay, it's just ordinary community algebra in a non-trivial tensor category. Okay, this is the algebra side of the story. There is also geometric side of the story. For the time being, I will do it very quickly. Okay, I think the most fundamental one is after the development of after the discovery of monster moonshine, Igor Frankel already noticed that the VOA can be used to study CFT. And also the Siegel's definition also plays some role, well, independent by Kontsevich. It says that, well, conformal field theory is some kind of a symmetric monoidal functor from board 2 to topological vector space, okay? Category topological vector space. Categorical language, okay? So this picture to give you some idea about this functor, it just says that if you have a destroying the 3 circles, it maps to 3 tensor product of closed string, the Hilbert space of closed string, and the similar for the codomain, right? And the morphism is for the cobordism, it maps to by the functor map to a linear map, linear operator between 2 Hilbert space. Okay. Well, the problem of the Kontsevich-Siegel's definition is that the quantum field in physics usually associate to a point in the space-time. They do not live in the Kontsevich-Siegel's definition in the direct way, because Kontsevich-Siegel definition involve a boundary component. So the modification of this definition was needed. The idea is to replace the Riemann surface with parameterized boundary by parameterized punctures, which was originally proposed by Vafa, physicist. Okay, and if you do that, you also have to replace the codomain by replace Hilbert space by graded vector space. Okay, this is done in Huang's Radical thesis. Okay, and the fundamental result in this direction is similar to Joule's thesis. Joule's thesis is appeared in the 1990s. Okay, in the same year, Huang's finished his thesis. So both theses play a very important role in the development of the mathematical theory of conformal field theory based on the permutation theory of VOA. So what Huang's theory says is that VOA is essentially just equivalent to algebra over a complex analytic version of the 2D operator. It was reset in this case because the algebra over this operator usually is called the E2 algebra. Okay, so VOA is nothing but a complex analytic E2 algebra. Basically, that's I'm expressing it using modern language. Okay.
So what is E2 algebra?
E2 algebra is the algebra over 2-disk operator. It's just tell you that it is the algebra such that it has a lot of multiplication, and the multiplication was controlled by a disk or a sphere with 3 punctures. Okay, that's essentially a pens. Okay, pens dragged to the infinity. Each boundary component dragged to the infinity. It just tell you that okay, this algebra have a lot of multiplications. Okay, but these multiplications are all connected to each other on the modular space of Riemann surface. Okay, the multiplication is controlled by pens. Okay, but it's a puncture, a sphere with 3 punctures. Okay, 2 punctures is coming in and 1 puncture is going out. Okay, that's called operette. Okay, yeah, I won't go through the detail. Let me just skip the detail because I'm just want to give you a bird's view of the historical.
Okay.
Yeah. Let me skip this. Juan also showed that if you have a puncture to the to sphere, but originally Siegel's definition is a boundary component. How to move from boundary to a real hole can be done via an algebraic version of a completion. So this is very important. Two important work also play an important role for the future development. Okay. And the next important thing is that you can generalize the closest CFT or closed string theory to the open string theory by including open string. That's that's natural development. I won't go through the detail here, but this is one of the important things. However, once you do this generalization, you can really study the boundary CFT and the open string CFT, which is nothing. It catch the mathematical structure on the boundary CFT. That means you can have a boundary field. The boundary field have OPE on the boundary. For example, like this, you have 2 fields. You can do the OPE as ordinary OPE, but since because the puncture are restricted to the boundary, you can on a complex plane you can restrict the boundary to the real line. So the field insertion become a real number now. Because they're a real number, you don't need to worry about the multi-valueness. So the power here can be real number. It's not necessarily an integer. Okay, that make the problem looks a little complicated. Okay, so also in the OPE is not necessarily integer. This looks make a lot of algebraists feel like, oh God, this is so complicated, because algebraists in mathematics prefer integer power series, formal variables, right? You study power series, but now it become not integer valued. However, this is a very important observation, because in the development of the conformal field theory, for many years, it stopped the physics to go beyond the integer power. It's really, I think it's really a convention or tradition, okay? But this really stopped mathematicians for many years because of this reluctance to move on to a not so familiar territory. But this is very important, because many or most physics is interesting example appeared in physics involve non-integer power. Okay, so this is a remark. So this is some kind of a real analytic E1 algebra. I just want to make a comment. Okay, it's the 2D with no puncture, with only puncture on the boundaries. That's to make an operette. This is the algebra or operette called the open string VOA. Okay. And you can do further things. Consider the bulk one, which is, the conformal, the VOA is a chiral. But now you can consider the non-chiral version called the full field algebra, which involve not only the complex number Z, but also involve complex number Z bar. This makes the theory much more complicated, but I won't go through the detail. But this just tell you there is a non-chiral version of VOA. This can be viewed as a non-chiral version of VOA. A typical example is that you use one VOA tensor another VOA. Okay, but on the second factor, in the second factor, all the field variable are necessary to be anti-chiral. Okay, so that give you an example of full field algebra. That's some kind of real analytic tool, E2 algebra. Then what you can do is that you can combine full field algebra and open string algebra to form a so-called boundary box CFT. Okay, there are some field on the boundary, there are some field in the interior, some field it represent the closed string, open string, and some other field represent the closed string. So this is an open closed theory. Now you can combine them together. Okay, you can combine them together. You got an open closed field theory. That's quite complicated. Okay, but this geometric side of story is important, is necessary, and to construct the whole conformal field theory. Now, I want to unify the algebraic and the geometric approach, especially after Huang's theorem of modular system category. Okay, this approach after Huang's big theorem on the modular system category, which says that given a rational VOA, its representation category is a modular system category. Okay, combine this theorem together with what I said of the other one for rational VOA, a VOA extension of V is equivalent to a committee algebra. Okay, and also the geometric side of story. I just sketched it. Okay, I didn't show you much detail. Then we obtain, combining all three together, we obtain the categorical characterization or classification of conformal field theory. Okay, over rational VOA. Okay, this result was preceded by Fuchs, Runkel, Schweiger in their FRS approach. Okay, in which they introduce simple special Frobenius algebra A in the mod V in the representation category of rational VOA, and use the state sum construction to construct all the structure constants of the CFT. Okay. All right. So let me. But this construction is a little complicated. I want to show you an equivalent one. The equivalent classification or characterization is somewhat simpler. So let me present this result. This result says that an open closed CFT over rational VOAV is a triple. Okay, so you have a closed theory, which is a committee symmetric Frobenius algebra in the Drinfeld center of mod V, and you also have open theory, which is a Frobenius algebra in mod V. You also have another data. Another data simply tell you how the open string interact with the closed string. Okay, and satisfy two conditions. One of the conditions looks like this. The third next condition look like this, and it's done. Okay, no more condition. So this is just the simplest mathematical description of the open closed CFT you can get. You can see that they're already quite simple, right? Already quite simple. Yeah, you can even squeeze the size of the font. You can probably squeeze them into one page. Anyway, it's already very simple, but it's not simple enough. Okay, I want to give you some idea that physicists might get horrified. How could this be possible? Because the mathematical structure of a conformal field theory is very complicated. For example, the Carty condition. Look at this. The Carty condition looks like this, right? How it was derived? It was derived by a real geometric condition. The Carty condition says that two cobordisms are essentially the same. I'm not going to show you why it's the same. But on the left side, it's only involved open string, because this says the open string split into two open string and switch order, okay, change positions, then fuse again. This is only involve open string, but this involve closed string. It says that the open string map to closed string, then map to open string. So this is non-trivial condition, okay? But if you write down the non-trivial condition, well, it looks like this. It's very complicated, okay? So what the mathematician will do, I want to emphasize that this condition have never been written down in physics literature. Only a weaker version was written down in physics literature, okay? I guess it's only because it's too complicated, so it's never written down. But once it was written down, using the mathematical theory, it will eventually simplify to this one, okay? So the language simplification is very amazing, okay? Only after you can do that, a lot of things can be proved. Okay, after this precise mathematical formulation of the open closed CFT, you can prove very strong theorem saying that the open string, the closed boundary CFT, okay, if it is A, the box CFT is nothing but its center in a categorical sense. Okay, you can even prove other formula. Let's say two boundary are Morita equivalent if and only if their box is same, so on and so forth. There are many other simplifications can be done. For the time reason, I probably won't be able to say much about Okay. Okay. Maybe just briefly. After this development, after the mathematical theory was fully established, you can study defect. Okay. At the very beginning, Fuchs, Runkel, Schweigert, Fröhlich made the first fundamental progress using their FRS formalism of 2D RCFT. In this formalism, everything can be made explicit. The domain wall simply can be defined, a defect between two block face can be defined as a bimodule. Okay, and from there, further simplification was introduced by Davidov and further work by all three people. We simplify the mathematical language of RCFT by using a powerful categorical language called internal hop. Okay, I don't have enough time for this. It just say that everything you can find in the CFT. This is the box CFT, living in a 2-cell. This is the domain wall CFT, living in the 1-cell. This is the 0-cell, okay, living on a 0D domain wall. Everything is internal hop, okay? So this simplification is pretty amazing. Tell you everything is internal hop. Then you can do the simplification. Because everything is internal hop, you can reduce the data to a single fusion category, or is enriched version. Okay, the enriched version, all the hop is replaced by internal hop. So this dramatic simplification was made possible after that. Because of this simplification, you can finally talk about the category of conformal field theory. Okay, because you look at, you can have one conformal field theory on this side, another conformal field theory on the other side, but on the one side, everything was reduced to a single fusion category. On the other side, it is also reduced to a single fusion category. Everything else is internal hop. It can be recovered from other data. And what's on the domain wall between those two CFT? You can simply reduce the data to bimodule of A and B. Okay. As a consequence, the category simply is a consistent object which is given by multi-fusion category, and the one morphism given by bimodule. It's a dramatic simplification. Okay, you can even make it simpler. You can make it simpler by showing that this is nothing but a close-like category of the trivial 3 category. Okay, I changed this setup a little bit. It's called the 2D quantum liquid because it's already slightly general, more general than CFT. Okay, but yeah, that's the end of my talk. I just want to show you that only after the simplification of the language, the category of rational conformal theory can be computed within a slightly bigger category. Okay, slightly more general notion called quantum liquid. All right. Thank you.
Thank you very much. So now we have a discussion time. I want to accept several questions and comment. So do you have any comment or question?
Yeah, excuse me.
Yes.
In some OP formula in your talk, there appears some real parameter K, right?
Their parameter of K, what do you mean?
K, yeah. In some OP formula, which appeared in your during your talk, some real parameter K appears, not even rational number, right?
Oh.
So I'm wondering why such irrational number appearance irrational number is consistent with rationality of VOA.
Oh, yeah. I need to apologize for the rational CFT. Only the rational number appeared. When I write this slice, this slice is not restricted to the rational case.
Okay. So rationality requires parameter K is rational number.
Rational number.
And so another question is, do you know the example where not irrational number K appear? Example of CFT where you need irrational number K?
Well, to be honest, I don't really know. But
that's only mathematical possibility?
Yeah, it's only a mathematical possibility. I don't really know any example that K is irrational. Let me see. But I believe that if you work with the Heisenberg, if you work with Heisenberg VOA, it is possible to using irrational K to construct an example of open string VOA. I haven't tried that, but I believe that's possible. I haven't tried that myself because that theory is definitely irrational. Not only irrational. So on the level of a VOA, you can make it the theory really wild. But if you want to prove convergence of a higher genus, you have to restrict to rational. For now, at least. But for irrational, you probably still need some cofinite condition, which is in order to prove the convergence of a higher genus correlation functions.
Yeah.
So if K is really wild, I doubt that you can prove the convergence. But if you only restrict to genus 0, it's possible. I think it's possible to have an irrational number. But that's just my wishful thinking. I don't really have any example. Yeah.
Okay. Thank you.
Yeah. You're welcome. That's a very good question. That's to prepare this talk, I really should say K is a rational number because I restrict my talk to rational case. Yeah, this causes confusion. So I apologize for that.
Other question? So I have a very fundamental question. So you use somehow skeleton. So what is the topological skeleton? What is the example of skeleton?
What is the example of what?
Skeleton. You often use this term skeleton.
No, I didn't. No, I didn't get to what's the word? Kyoto?
Skeleton.
A skeleton. Oh, the last slice. Yeah, because I skipped too many things. The skeleton was introduced in the previous slides, but I think I looked at my watch. I don't have time to explain it. What happened is this, okay? If you look at the structure of conformal field theory, it contains a lot of data. But however, a lot of them can be summarized by using the category. Okay, so if you realize all the data of rational CFT, you need a VOA. Okay, but all the rest of data can be summarized using categories. So either they are object in the fusion category, and or their internal harm in their dream field center, like all this. So all this internal harm are living in the dream field center of B. They're categorical. They can be categorically defined. So what I call the topological skeleton is that if you ignore the VOA, everything else are categorical. So I will give a name for this categorical data. I will call it the topological skeleton. Okay, then the topological skeleton can be dramatically simplified because if you ignore the VOA, everything else are categorical. And the data can be rebuilt from a single data of fusion category. That's make the simplification so dramatic, such that one are able to talk about the category of rational CFT. If you have if you include the rational CFT in this language, then you are in trouble. It's very difficult to talk about what the CFT means because there's so many data in it and how to define the category of CFT. That's become a difficult. Okay, so only after this simplification, dramatic simplification, you can make life much easier to talk about to study the category of them, and eventually you can even prove that category is the subcategory of this one. The subcategory, the category of all rational CFT is a subcategory of this very simple category. Of the three vectors. Yeah.
Thanks very much. So other comment or question? Maybe there is no comment. Thank you very much.
Okay, thank you.
So then in the next session, Conrad become the session chair, and who is the next speaker?
So I will be the chair only for the next speaker, right? Because
no. Next. Just a moment. You are a chair of next two sessions until January.
Right? Yeah.
Yes, because only the speaker of long talk become session chair.
Yeah, sure. I'm gonna chair the next 2 sections, right? Yeah.
Yes.
Okay.
Next,
Problem. Yeah. So we'll come back. What? We almost need to come back in 1 minute, right?
Yes, only 1 minute. So
only 1 minute. I see. So our next speaker is Bias. Can you share the screen now?
Okay, can you hear me?
Yeah.
Okay.
Okay, let me take a look at the time. Yeah, I think it's 2:20 now. It's good time to start. Okay, so our next speaker is Ansi Bai, who is from Southern University of Science and Technology, and today he's gonna talk about he's gonna talk about a 2 categorical interpretation of the reconstruction theorem for weak-hof algebra. Yeah, let's start. Yeah.
Okay, thank Liang. Thank the organizer for giving me the honor to speak at this SUSTech-Nagoya workshop on quantum science. I'm Ansi Bai, and today I'm going to talk about this 2 categorical interpretation of reconstruction theorem for weak-hof algebras. This is based on a joint work with Zhihao Zhang, who will speak after me, and this is our work in preparation. Well, the notion of weak-hof algebras, or WHAs, originates from the motivation to describe certain symmetries in quantum field theory and operator algebras. As a quantum symmetry, WHA, along with their representations, have wide applications in the studies of both quantum phenomena and novel algebraic structures. Our goal today is to give a new interpretation or generalization of a basic theorem on WHAs. This theorem is called the reconstruction theorem, or Tanaka-Crane duality for WHAs, of which the original version is due to Professor Takahiro Hayashi, who is also from Nagoya University. This theorem establishes a strong relation between WHAs and their representations. I hope you can get interested. Okay, I will first tell you some basics on WHAs, and secondly, the reconstruction theorem, and finally give you my interpretation. So this is just a 1-page introduction to WHAs. A weak-hof algebra is a vector space H together with 5 linear maps M, U, delta, epsilon, and S, where H, M, U is a finite dimensional associative algebra, and H delta epsilon is a co-associative co-algebra. And delta preserves multiplication. That is, delta is a homomorphism of algebras, but it only does not preserve the unit. And M, U, delta, epsilon satisfy some certain other compatibility conditions. And the antipode S is an algebra anti-homomorphism and also a co-algebra anti-homomorphism, subject to certain compatibility conditions. Of course, you don't need to recite all of these, and I will give you a short example of weak-hof algebra. Let G be a finite group point, that is, a group point whose home set and the set of objects are all finite. Define a weak-hof algebra CG to be the span of all morphisms in G, with the multiplication defined to be M G1 tensor G2 to be G1 G2 if G1 can be left composed to G2 and to be 0 otherwise. And the unit of this algebra is defined to be the sum of all identity morphisms. The delta of G is defined to be the copies of G, and the epsilon of G is defined to be 1. And S of G is defined to be G inverse. So let me remark that when G has only one object, that is a group, then CG is the group algebra and is a basic example of Hopf algebras. An interesting fact is that there are two canonical subalgebras of a WHA-H. To see this, first know that there are two projections, PL and PR, and from H to H. And here we used Swiller's notation, delta 1, and to be 1, 1, tensing 1, 2. For example, in the expression of PL, we map X to the following element in H. We first multiply X with the first factor with delta 1, and then we apply epsilon to get a number. And then we multiply this number to the second factor of delta 1. So we get an element of H. So then we have the following facts. First, the imagers HL, which is defined to be the image of PL, and HR, the image of PR, are closed under multiplication and contains 1. Thus are subalgebras of H. Moreover, they are separable. Secondly, the algebras HR and HR are anti-isomorphic. That is, HR is isomorphic to HL. Thirdly, the algebras HL and HR mutually commute with each other. That is, for X in HL and Y in HR, we have XY equals to YX. Fourthly, there is SHL equals to HR and SHR equals to HL. That is, the antipode transfers the two subalgebras to each other. Okay, let us see the case groupoid algebra. For the groupoid algebra CG and for G from A to B, a morphism in G, the two projections read PR sending G to the identity of A and PR sending G to the identity of B. And consequently, HL equals to HR equals to the span of all identity morphisms. The projections PL and PR are hence called the source and target maps respectively, while the subalgebras HL and HR are the source target algebras. Well, in this case, the source and target algebras, as you can see, are commutative algebras. Indeed, they are just copies of the complex number, right? However, this is not true in a generic WHA. Let me say something about the representation category of a WHA. Let H be a WHA and let H mod denote the category of left modules over H. Then the aforementioned facts on the two subalgebras lead to the following statement. There is a forgetful functor U from H mod to HL tensoring HR mod. Here, the functor U acts in the following way. Given a left H module V, the left HL tensoring HR module UV has the following HL tensoring HR actions. It has commuting left actions from XV to X acting on V, and from YV to Y acting on V for X in HL and Y in HR. Well, note that HL mod HL is a monoidal category. And sorry, by HL mod HL, I mean the category of HL bimodules. And I will use this notation to denote the category of bimodules. Okay, so HL mod HL is a monoidal category whose tensor product is given by the relative tensor product over HL. Using axioms of WHA, one can also show that the category H mod carries a monoidal structure. Well, this fact may not be very surprising to those of you who are acquainted with Hopf algebras, since Hopf algebra is just the special kind of a weak Hopf algebra, and the category of representations both carry a monoidal structure, and they carry a monoidal structure in a similar way. Well, for those of you who are not acquainted with Hopf algebra, you can just view it as a fact. And secondly, the functor U is monoidal. So we are now prepared to introduce the reconstruction theorem. Indeed, I have introduced the right squig arrow in the following figure. From a WHA-H, we get a pair, we get a monoidal category H mod, right? And we get a separable algebra HL, which is the subalgebra of H. And we get a monoidal functor from this monoidal category H mod to the bimodule category of this separable algebra HL. So the reconstruction theorem simply says that this right squig arrow has an inverse. So what does it mean? what should the inverse of the right square arrow achieve? Well, it should read from a monoidal category C and from a separable algebra R and from a monoidal functor F. Well, can we get a WH such that C equals to H mod as monoidal categories, and R is equal to the subalgebra of H. And finally, this functor U is isomorphic to F. Okay. Are there any questions? Please interrupt me. Now I briefly will show you how the left square arrow can be realized or prove the theorem. Okay, so now we start with, recall that we start with a pair CF, and first we define a long forgetful functor F tilde from C to the bimodule category of R, and then through the lowercase of F to VAC, where the lowercase of F acts in the following way. It forgets the R bimodule action and preserves the vector space. Then there is a standard construction which defines H to be the endomorphism algebra of F tilde, such that H mod equals to C as categories. And this is standard and does not involve Wyckoff algebra. So it still remains to give the Wyckoff algebra structure on H. However, I will skip most of it and only get you to see that there are two subalgebras of H, isomorphic to R and R op respectively. For R in R, define natural transformations R sharp and R flat from F tilde to F tilde as follows. For an object X in C, we define the component R sharp X to be the linear map from F tilde X to F tilde X, sending a vector V to V acted by R on the left. And we define R flat X to be a linear map F tilde X to F tilde X, sending a vector V to V acted by R on the right. And here, the left and right actions of R on V is defined in the bimodule Fx. And recall that Fx and F tilde X are the same as vector space. So we can view a vector lowercase v both in Fx or in F tilde X. And then we define sets. The uppercase R sharp to be the set of all R sharps, and R flat to be the set of all R flats. Then it is now hard to see that R flat and R sharp in H are subalgebras isomorphic to R and R op respectively. Now, surprisingly, if we work out all structures of H, which allows us to compute HL and HR, then HL equals to R sharp and HR equals to R flat. Thus, we have the functor U is isomorphic to the functor F. So we have shown the left square arrow comes. We have shown one side of the cosine inverse, right? The other side of the cosine inverse is not hard to verify, and we leave it to the intrigued audience. And up to some technical issues, we have proved the reconstruction theorem. That is, we have reconstructed a Wyckoff algebra H from a pure categorical data F from C to R bimod. So for the rest of time, let me give you an interpretation of this theorem. I want to emphasize that this reconstruction theorem is essentially a two-categorical phenomenon. Define the following two-category 2-vec. 0, 2, 1, and 2 morphisms are separable algebras, bimodules, and bimodule maps, respectively. Well, more precisely, we define the one-hom category from R to R prime to be the category of R prime R bimodules for separable algebras R and R prime. And here is just a convention where you put R prime and where you put R. And I choose this convention. And composition of one morphisms are given by relative tensor product. More precisely, we need to give a composition functor, right? And the composition functor is defined to be the relative tensor product over R prime. Then it is easy to see that the monoidal category, which is the category of bimodules over R can be viewed as the looping of the one object full sub2 category R of 2vec, as is shown in the graph below. That is, we only choose one object of this 2 category, and then we include all the one morphisms, anal one morphisms of this one object, and we get a monoidal category, which is precisely R mod R. In particular, the data of the pair CF are precisely of the data of a pair BC and F prime, and here BC and F prime are defined in the following figure in an evident way. So BC is just a 2 category with one object, and its endo one morphisms are objects in C, and F prime can be obtained by F and this inclusion. And you can check that the data of this pair and the second pair are identical. Thus, it is equivalent to say that the reconstruction starts really from the pair BC and F prime, which is a 2 category data. A natural question is, can one reconstruct some algebraic data from more general 2 functors to 2vec? Well, let me give you a remark. Why do we care about 2vec? The 2 category 2vec is too equivalent to the category of finite semi-simple C-linear categories, C-linear functors, and natural transformations, which deserves to be viewed as a categorification of vec. So it is a very basic 2 category. Well, the answer to the previous question is yes, we can. Let D be a 2 category and let U from D to 2vec be a 2 functor. And we can reconstruct some algebraic data from this pair, D and U. Well, we denote the home categories in D by DAB, and the local one functors of U by UAB. And recall that UAB sends a local one home to a local one home of vec. And then we have a one functor, UAB tilde, sending DAB to the category of UB UA bimodules, and then use the lowercase of f to vec. Then the standard construction tells us that the algebra HAB, which is defined to be the endomorphism space of UAB tilde, satisfies that HAB, the category of left HMAD modules, are equal to DAB as categories. Moreover, there are algebra homomorphisms UB to AHAB and UA up to HAB. As a matter of fact, the whole algebraic data reconstructed from U can be formulated. I will just go through this definition, but you need not recite this. So I call this algebraic data a Wyckoff algebroid, following a paper by Day and Street, which they define Hopf algebroid. So a Wyckoff algebroid H consists of the following data: a set of objects of H, and for objects AB in of H, there is an algebra HAB, and for objects ABC, a generalized comultiplication delta ABC, and for a counit epsilon A from HA to K, and for objects AB, a generalized antipode SAB sending HAB to HBA. And this generalized comultiplication delta AB and the counit epsilon make the co-associativity and co-unitality hold. So the set of HABs indeed forms a co-category, and they satisfy some other compatibility condition that I will not go through in detail. However, let me stress that the antipode is a map from HAB to HBA, and it is an algebra anti-homomorphism compatible with the co-multiplications, and that satisfies certain conditions. Well, a one-object Wyckoff algebroid is a Wyckoff algebra. So what I'm basically saying is that there is theorem one can reconstruct a Wyckoff algebroid from a pair D, U, where D is a 2 category and U is a 2 functor. The converse is also true. Given a Wyckoff algebroid H, there is a pair mod H and FH, where mod H is a 2 category and FH is a 2 functor. So this theorem generalizes the reconstruction theorem for WHAs. More precisely, if we take D to be a one object 2 category, then we recover the latter. This provides a way for understanding the original theorem, especially the appearance of the category R mod R there. Let me skip some details about this Wyckoff algebroid. Just let me focus on the latter two. So some examples of Wyckoff algebras can have its Wyckoff algebroid counterpart. In particular, the Wyckoff algebra studied in Kitaev and Kohn is indeed a substructure of Wyckoff algebroid, which can be used to describe more general boundary excitations in level 1 models. And this is the starting point of my collaborator and me to study things like Wyckoff algebroid. That is, we need to clarify algebraic structures in Kitaev and Kohn and delve into it. So thank you all for listening. And I would like to thank Liang Kong, Zhihao Zhang, and members in my group, and Shang Sui. Thank you.
All right. Nice talk. And shall we thank the speaker? All right, it's a problem section. So anyone have any questions? Does anyone have questions?
I'm Takahiro Hayashi. Nice talk. And I think your construction have
Nice to meet you.
already have an example. Someone write a paper probably related to your work. More concrete situation. Someone constructs some kind of algebraic system like you. But I'm sorry, and I cannot remember the paper.
Okay.
The name of the paper. Sorry.
Oh, I see. Around what year? Is recent or many years ago?
Many years later.
Many.
Before.
Oh.
I see.
Thank you.
Do you have any keywords to?
Sorry, I try to remember, but I need more time. So sorry.
Okay. Thank you. I will be glad to hear that there is a similar work, and I'm glad, and you can tell me later.
Yeah. And I think probably you know there's a generalization of Wyckoff algebra. Wyckoff algebroid. So your name is, I think, Hopf algebroid is not a good name.
What you mean is that my Wyckoff algebroid already has another meaning?
Yeah.
Oh,
By
okay.
algebroid and Hopf algebroid they are some kind of generalization of Wyckoff algebras.
Okay. I will check that.
Yeah.
I already heard something like Hopf algebroid, and I think that Hopf algebroid already have some meaning, but I haven't seen Wyckoff algebroid. But I will search it. Thank you for your comments.
I think that the name is there are a lot of confusion about the name because Wyckoff algebra also have a name called a quantum groupoid, right?
Yes.
So, yeah. So in that spirit, if you apply that spirit, you will get the quantum groupoid, doubleoid, right? Yeah. Anyway.
Yeah, indeed.
All right. Any other questions? Well, if not, let's thank the speaker again. So we can take a few minutes break before the next talk, which will come in 7 minutes, I think. Yeah, we will start. 6 minutes. We will start from 2:50. All right. So, yeah. See you guys later. So is the next speaker here? Let me take a look.
Yes.
Oh yeah. Can you share the the screen now? Do a little preparation. Yeah. Oh yeah, very nice. So may I ask how to pronounce your name?
Shintaro Yanagida.
Nagaji. Okay, Nagaji. Since they still have 2 minutes, do you know the Chinese letter of your name? Or is that easy to type? From
Wait a minute.
Okay.
This one is Yanagi.
Oh, I see. I see. Yeah. I see. Yeah, got it. Very nice. Yeah, I see. I see. Oh, that's very nice. It looks like your interest is very close to what I talk about.
Yes.
Integral models. Yeah, okay, I think the time is ready. So let's start the next talk. The next talk will given by Shintaro Nagaya. And he's gonna talk about the introduction to Macdonald polynomial from the viewpoint of a quantum integral model, integral systems. Yeah, let's start.
Thank you very much for the introduction. And as an organizer, I'd like to thank all the participants and all the speakers for joining this workshop. So my talk is, as the title says, so I will give some introductory talk on Macdonald polynomials. Since in this workshop, there are several talks, especially on Wednesday tomorrows, so those are related to Macdonald polynomials. And my talk is divided into 3 blocks. And the first block is an introduction of the most basic one, the Macdonald polynomials of type A and its relation to quantum integral systems. And that word of type A means that it is a symmetric one. So anyway, so this one is some symmetric polynomials. And in the end, I will talk, Macdonald polynomials of type A is nothing but some deformation of sure polynomials with some parameters. So let me start with this classical object sure polynomial. So here is some global notations of my talk. The symbol X denotes a set of commuting n variables, x1 through xn. And Sn denotes the symmetric group. And Sn acts on the module of the polynomials, the Laurent polynomials of variable x1 through xn with integer coefficients by permuting the indices of these x variables. And I denote by this symbol the module of symmetric Laurent polynomials. So the polynomials, Laurent polynomials that are preserved by this Sn action. And I also denote by p plus, it's a little bit strange notation, but this symbol denotes a set of dominant weights of type n minus 1. But the actual definition is that just a dominant weight is sequence of integers of xn, which is not non-inclusive. So any such a dominant weight lambda, we have so-called sure polynomial, which I identify as lambda x. That the explicit definition is the ratio of these determinants. And it is known that these sure polynomials form an orthogonal basis of this module with respect to the inner product given by some integral over the algebraic torus of dimension n with the weight function given by this equation. So anyway, we have some inner product and sure polynomials are orthogonal with respect to this inner product. And some of you may wonder why we are considering the integers here, that restricting lambda to a non-positive, to a non-negative entries, then dominant partition is dominant weight is nothing but a partition. So we have the usual sure polynomial. This is a genuine polynomial, not a Laurent polynomial. So anyway, so in this standard setting, the sure polynomial is gives a basis of this module of symmetric polynomials. And sure polynomials is known to have a nice property called the triangular expansion. So here I denote by m lambda. This is another basis of the symmetric polynomials defined by the orbit summation, and it is called the monomial symmetric polynomial. And this is anyway a basis of this space module, so we can expand the sure polynomial in terms of m lambdas. The statement is that in this expansion, only partitions which is equal or less than the lambda, the index of the sure polynomial appears. So here I used the so-called dominance ordering, and this is the definition, and this is defined by this expression. But anyway, we have some ordering, and on that ordering we have this lambda or something less than lambda terms appears in expansion. So here is some example of that triangular expansion. Sure polynomials in terms of symmetric polynomials. So this is a property of sure polynomial, but I want to note that we have how to say. So anyway, so we have two properties of sure polynomials. The one thing is triangular expansion, and another is orthogonality with respect to the inner product. But these two properties can be used to define uniquely the symmetric polynomial S lambda. So these two properties give some characterization of the sure polynomial. So this is a very short introduction to sure polynomial, but what I want to explain next the Jack polynomials, and so in a nutshell, Jack polynomial is some deformation of sure polynomial. So here is some formal definition. So Jack polynomial associated with a partition lambda having some parameter beta. This is a complex parameter denoted by the symbol. Is a symmetric polynomial which is uniquely determined by the two conditions, the properties. The one is the triangular expansion, and the other is the orthogonality. So these two properties are the same with similar to this sure properties. But here in the orthogonality, I used a deformed inner product, deformed by the parameter beta. So I switched the inner product 1 to some inner product beta. So this inner product is given by this integral, but in the integral we use the weight function depending on parameter beta. So we have some deformed inner product, and accordingly we have some deformed basis of the symmetric polynomial space. And if we take beta to be 1, then this in the product reduces to sure in the product. So the definition in the Jack polynomial whose parameter beta is set to be 1 is nothing but sure. So we see that Jack polynomial is a beta deformation of sure polynomial. Here is some expressed examples of Jack polynomials for small functions. So to expanding by the monomial symmetric polynomials, we have some coefficients including beta. And if we set beta to be 1, then these expansions reduce to expansions of sure polynomials. And one bad news is that unlike the sure polynomial, which was defined as the ratio of determinants, the Jack polynomial has most simple formula. There exists some expression formula, but that is a little bit complicated one. A nice news is that the special case, the one variable case, we have some expression formula in terms of the Gauss hypergeometric function or series. So in the one variable case, so n is set to be 1, then the index lambda, a partition, is nothing but non-negative integer L. So let me rewrite lambda by L. Then the Jack polynomial of indexed by L, JL, is equal to the Jacobi polynomial with some specialized parameters. The Jacobi polynomial is defined by this expression. So 2f1 denotes the Gauss hypergeometric series. And here we have two parameters alpha and beta. The L denotes the degree of the polynomial. So anyway, so we have a non-positive entry in the 2f1. So this series terminates, and we have some polynomial object L. So this is the definition of Jacobi polynomial with parameter alpha and beta. So this is a hypergeometric polynomial, and it satisfies some orthogonality with respect to some product. So it is called hypergeometric orthogonal polynomials. And the Jacobi polynomial sits in the very famous ASCII scheme of hypergeometric orthogonal polynomials. This diagram. And here is the Jacobi polynomial. So anyway, a Jack polynomial of one variable case is some specialization of Jacobi polynomial in the system. And in Yamaguchi-san's talk tomorrow, there will be a Q analog of this diagram. So it is called the Q ASCII scheme for that. So anyway, what's going back to the general the Jack polynomial of multi-variable case, I want to mention another characterization of the polynomial. I have explained the characterization using triangularity and orthogonality. And instead of orthogonality, we can also use the eigenproperty as a characterization of Jack polynomials. Here, eigenproperty means that Jack polynomial is an eigenfunction of some operator denoted by HCS, and the HCS is given by this expressed formula. So it is anyway some differential operators having parameter beta, and so it is named the gauged curve Sutherland Hamiltonian. I will explain why what this terminology means, but anyway, let me proceed to this topic. So HCS, it is some differential operator, sits in an infinite family of mutually commuting operators, O1, O2, 3, and OK in general is defined by this expression, built up by the so-called rank operator. And in fact, Jack polynomials J lambda are joint eigenfunctions or simultaneous eigenfunctions of this family of operators. Okay, so J lambda is simultaneous eigenfunction. So OK acts J lambda, then the result is J lambda times some complex numbers. So J lambda is an eigenfunction of all the operators. Now in the next slide, I want to explain this terminology, Sutherland Hamiltonian. So it is related to some explicit quantum model, quantum dynamical model. In 1971 paper, Sutherland introduced the so-called Sutherland quantum Hamiltonian, given by this expression and denoted by H prime. So here. So this original Hamiltonian describes some quantum mechanics of n particles on a circle list with the interaction potential proportional to the distance of the squared distance of two particles. So this is a potential. And so this H prime, the original Hamiltonian, quantum Hamiltonian, was introduced to quantize the Karl-Mozart classical integrable system. And this is a very famous integrable system. But anyway, the original Hamiltonian H prime has a ground state psi 0 given by this formula. So modding out by this psi 0, we have the gauged Hamiltonian HS. So this is a gauged Hamiltonian HS. So HS and the original H prime JS related by this relation. And going back to the Jack polynomial, and recall that in Jack polynomial is an eigenfunction of HCS. So Jack polynomial for general function lambda describes some excited states of this quantum system. So this is the physical meaning of the Jack polynomial. Now I finished the introduction of Jack polynomial, so I want to go to the McDonald case. But in McDonald, polynomials are also introduced as some eigenfunctions of some operators. And then, so we need some that operators. To do that, I should mention very important work of Rasmus on 1987 paper. So he introduced what is now called the elliptic Wissner's operators. So this is a Q difference operators with elliptic function coefficients. So the expressed form is like this. So he introduced n operators denoted by dx r. So this operator acts on the functions of x. And it has three parameters, q and t and p. So let me explain the meanings. The parameter q appears here. TQXI denotes the shift operator, multiplicative shift operator on xi. So the variable xi is multiplied by the shift parameter q in the function. So here is some q difference part, the q shift part, and we have some coefficient. Here theta denotes some theta function, and this theta function has elliptic node p. So p is some elliptic parameter. Okay, p appears here, and the third parameter t appears here. So anyway, the operator dr, the operator has three parameters and acting functions on x. The statement of Wissner's is that this family of operators commute with each other. So we have this relation. And there is a big problem to find and study the joint eigenfunctions of this family of commuting operators. But there are very important progress on the problem, but let me skip this point and go to the McDonald case. McDonald operators is defined to be some degeneration limit of the elliptic Wissner's operator. So recall that Wissner's operator drx has a parameter p, elliptic parameter p. And we take the limit of p to 0. Then we have some operator having only parameters Q and T. And using that from the definition of theta functions, we see that we can calculate this limit. The result is like this. So there's some rational equations up here. Since elliptic operators are commutative, this degenerate operators also commute. So this is a thing. But here is some non-trivial fact of this. So in this McDonald operators preserve the space of symmetric Coulomb polynomials. So this point is a little bit non-trivial. Then using the dominance ordering, we can find the basis of this space of symmetric Coulomb polynomials, satisfying some triangularity of expansion in terms of symmetric polynomials, and the joint the eigenproperty with respect to the McDonald Q difference operators. So this is some eigenvalues. So this basis is this is nothing but McDonald polynomial of type A. As in the case of Schur and Jack, the McDonald also satisfies orthogonality, and we can use triangularity and orthogonality as another characterization of McDonald polynomials. And here we should use some in a product depending on the parameters Q and T. The actual the weight function of the inner product integral is given by this formula. So the Q and T are here. And here is some explicit examples of McDonald polynomials expanded by polynomials. So here are some here in the expansion coefficient, some rational functions of Q and T appears. And from this expansion or from this weight function of the product, we can see how this McDonald polynomial behaves and parameter specialization or parameter degeneration. If we take parameter T to be equal to Q, then this polynomial seems to depend on the parameter Q, but it's actually independent of the parameter. So reduces to the Schur polynomial. So you can see that that if you take T to be Q, then this function reduces to be 1, and this function reduces to be 2, I think. So anyway, so P lambda Q and T for Q is equal to the Schur polynomial. Here is another degeneration limit. And if we take T to be Q powered by beta and take the limit Q to 1, then this polynomial, depending on parameter beta, is equal to the polynomial depending on beta. So in this sense, McDonald polynomial is a QT deformation of Schur and Jack polynomial. And that is what I want to tell you in it. So here, I have almost finished the introduction of McDonald. Here is some comment on the operators and parameter degeneration of operators. So it needs some technical care, but in the end, we can show that the infinite family of commuting operators O1, O2, 3, appearing in Karajero-Sazanato model can be reconstructed from the McDonald operators. Using the operator algebra denoted by QT here, and this algebra is what is called the quantum toroidal GR1, and also called the Dino-Karamiki algebra. And this algebra will appear in Panopons and Stockholm Wednesday tomorrow, I think. So anyway, I finished the introduction of the McDonald symmetric polynomials. So let me proceed to the second part. The second part is, anyway, some extension of the type A theory I explained so far to some general theory for general root systems. And that theory was established by McDonald. But before going to the general theory, let me explain the motivation to extend such a McDonald symmetric polynomial theory. Why we can expect such a general theory exists. So recall that we have an eigen equation for the McDonald polynomial, McDonald symmetric polynomial, for the difference operator of first order. So D1 P lambda is equal to P lambda times something. And let me take lambda, the partition lambda, to be the empty partition or the sequence 0 of zeros. Then the corresponding polynomial is not to be equal to 1. So this equation, the right-hand side is equal to just epsilon lambda, so some constant. The left-hand side can be calculated, and the result is as follows. So we have a non-trivial equality like this. So in the left-hand side, we have some x-dependent terms, but summed up, it is independent of x. And McDonald has found that there is some extension of this equality to any finite wide group, W finite. So the general equality looks like this. But anyway, if we take W or corresponding root system to be of type AN-1, then the wide group reduces to the symmetric group. And rewriting something a little bit somehow, these variables, we recover the original eigen equation of McDonald polynomial type A with constant version. So this generalized, this McDonald identity is actually the motivation to generalize the theory of McDonald symmetric polynomials to general systems. The point is that we should somehow construct the Q-difference operators, which are mutually commutative in terms of those general root systems. And here is the clue. We will use the so-called extended affine Hecke algebras. So let me explain in the type A case. So this is a reformulation of McDonald symmetric polynomials. So here is Sn, the symmetric group, and I regard it as a Coxeter group with generators Si. So Si is given by the adjacent permutation. So this can be regarded as a finite wide group. And this finite wide group can be extended to the affine wide group by an extra generator S0. We can also extend this affine wide group moreover to the extended affine wide group by another generator omega. This extended affine wide group, denoted by W, can also be regarded as a semi-direct product of finite wide group and the translation part of the weight lattice of the corresponding system. And associated to this extended affine wide group, we have the so-called extended affine Hecke algebra HW. I will not give the precise definition of this algebra, but to please understand that this algebra is a T deformation. It's just some deformation of the group algebra, the extended affine wide group W. So it has an algebra having the parameter T, and which is similar but a deformed one from the group algebra of W. And the point is that we can realize this HW algebra by the difference operators, so-called SUSTech operators, TIs. So I runs through 0 to n minus 1, and given by this formula. The statement is that the HW is realized as generated by Ti's and another operator omega G given by this expression. So anyway, we have some good algebras and good realizations. And using this realization of affine algebra, we can construct the Q analog of Danko operators. So this is the definition, Yi. So Yi is constructed from the generator, from heuristic operators and omega theta. And the fact is that these Q-Danko operators give the algebraically independent generators of the center of the extended affine algebra. Moreover, the McDonald Q-difference operator of type A can be reconstructed or can be presented as the elementary symmetric polynomial Q-Danko operators. So anyway, so we have reformulated the Q-different McDonald operator in the extended affine algebra. And this reformulation is very important since this argument can be extended to other root systems and W. And the general theory is built for some pairs of S and S prime, and these are affine root systems in the sense of McDonald. But there are actually three classes of pairs on which we can build a general theory. And there are some three classes. And the type A case sort of have explained so far corresponds to type 1 term, the class 1, with this choice of the pair. Yamaguchi-san tomorrow will talk of the type C check C, and this type sits in class 3. And the corresponding polynomial is called the Cohn-Wiener polynomial. So anyway, we have some, if we are given some pairs of affine root systems, then we can construct McDonald polynomials. And before going to the explanation, here is a classification table, the reducible affine root systems in the sense of McDonald. So type A is encoded by extended link diagram of type A. And here is the type C check C. And this corresponds to Cohn-Wiener polynomial. And so this diagram will appear in Yamaguchi-san's talk tomorrow. But anyway, this is the classification. So here is the outline of the general theory which I mentioned. So let us give a pair of affine variables. Then we can construct from S prime at the extended affine variable W, and the associated extended affine algebra HW, and its realization by heuristic type operators. Then combining or building up these operators, we can construct Q-Danko operators, and these are mutually commutative. And further, after some calculation, that we can construct explicitly in this family of McDonald Q-difference operators of type S and S prime given pair. So these are mutually commutative. And this family of operators act on the space of finite wide group invariant polynomials. So this space. And using the dominant ordering, we can find the basis of this space, satisfying the triangular expansion and the joint eigenproperty with respect to this family of operators. So the obtained basis is called the McDonald polynomials P lambda general. So lambda here runs over dominant of the root system we are considering. And in this general McDonald polynomial of general type has parameters q and t, but here t star was studied. Q is q, so just a shift parameter. But in general case, we have several t parameters. So I did not write t star. As I have explained for type A, in the type A DE case, we have only one t parameter, but in general, there are several t parameters. And the fact is that the number of t parameters is nothing but the number of W bits in the system S, in the affine root system S we are considering. And maybe this terminology will appear in Friday's talk, but anyway, the t star, the parameter t is sometimes called the Heckel parameters. So staying in the Heckel algebra. So anyway, the McDonald polynomials of general type have several parameters. And here is here's a hint for Yamaguchi-san's talk. So among the McDonald polynomials, the convided polynomials, the polynomial of type C has the most parameters, 6 parameters, meaning that we have 5 t parameters and 1 extra t parameters. So we have 6 parameters for convided polynomials. So anyway, we have some existence theorem of McDonald polynomials, but then we want to study the properties of McDonald polynomials. But in order to do that, so we need another caveat, the so-called DAHA, double affine algebra. I have no time to explain this one in detail, but using this one, we can show several things, including the orthogonality and moreover the explicit norm formula of the McDonald polynomials with the given inner product. And another property is the so-called duality formula. So this is a formula of the McDonald polynomials of index lambda specialized at some value associated to another partition and normalized in some way. This quantity is invariant under the permutation lambda quantity here. So this is a non-trivial equality, and this duality formula will appear in constances. And I think, yeah, this is the end of the McDonald, the very, very introduction of the general theory of the McDonald polynomials. So anyway, so here is a summary. So in the type A case, we have McDonald polynomial of p lambda x q and t, which is a symmetric function, a symmetric polynomial. And that polynomial is an eigenfunction of some Q difference operators, and it has the triangular property on expansion with respect to the monomial symmetric polynomials. And that polynomial theory can be generalized to some nice pair of affine root systems. Based on the extended affine Heckel algebra and the Q difference operator realization and constructed the McDonald Q difference operators. So here is the final slide. So my talk is almost finished. But here is some concluding remarks for some hints on the talks delivered on tomorrow. So I have explained orthogonality of Schur-Jack and McDonald polynomials using the integrals, but that inner product can also be described in terms of the power sum symmetric polynomials or functions given by this. So this is the case. In the McDonald case, we can reformulate the inner product by this simple formula. Not using integrals, we can introduce the polynomial by this simple formula. And this inner product will be the starting point of consensus. Another very important property on the McDonald operator of first type, of type A, is a so-called bispectral property. So this operator dx1 has another solution, a non-polynomial but a series solution indexed by the complex weight. So these are the sequence of complex numbers. And having parameters q and t and two variable sets q and s. And this solution satisfies the bispectral eigenproperty. And this will appear in consensus. What may not appear, I'm sure, but anyway, it is related to the consensus. And the final remark is the ring structure. The ring structure of the invariant polynomial ring. This one. So in the classical case, the sure case, if we take the product of two sure polynomials, then this one is again a symmetric polynomial, so it can be expanded by the sure polynomial. The resulting expansion coefficient is equal to the counting of the semi-standard tableau. This is a classical Littlewood and Richardson rule. And this error coefficients have some analog for Jack and McDonald polynomials of type A and even for McDonald polynomials of general type. Yamaguchi-san will give you some very complicated formula of this error coefficient for combined polynomials. So the most parameters is having 6 parameters. Very complicated formula here. And the final remark is that we can also consider a deformation of this multiplication, also by using some extra parameters here. And such a deformed ring structure may appear in consensus. But anyway, the time is up, so let me close my talk. Thank you very much for the attention.
Well, thank you for your nice talk. Okay, so now is a problem section. Does anyone have a questions? Yeah, maybe let me start with questions. So at the very beginning, well, maybe in the middle, you mentioned that a certain polynomial, the Jack polynomial, all this, have some physical origin from quantum integral model. But after that, you also introduce many other mathematical subjects. For example, hack algebra, double hack algebra, and hack algebra, and also the polynomial related to this. So I wonder that does this family of hack algebras have any direct physical meanings?
I don't know, and as far as I know, there is such study on the physical meaning of hack algebra. But I should mention that in very different context, hack algebras appears in physical context, of course.
Oh, really?
But these are fine hack algebra. I have not found in physical context.
Okay.
A fine one.
And these polynomials occurred in the physical context as some kind of eigenfunctions of a certain Hamiltonian, right?
Jack polynomials. Yes.
But all the others, okay.
So all the others doesn't seem to relate to some physical Hamiltonian. So we have operators, but we cannot say that it is a Hamiltonian of some physical model, as far as I understand. But they say that it is an integral systems because the family commits with each other. So. And in some sense, this so as the title of the reference paper says, so this operator was discovered by deforming or considering some relativistic analog of Calogero-Moser or Calogero-Sutherland. So it has some origin in physics, but the result is, as far as I know, apart from physical context.
And the tools to construct this kind of polynomials and are mainly from representation theory, right?
So in a sense, so McDonald polynomials give some give polynomial realization, representation of affine algebras.
Yeah.
This is one thing. But there is very little study on the whole what category of representation, the representation category of affine algebras.
Yeah, but I wonder this, even though I mean these algebraic stuff have a lot of representation theory. It's natural to look at it from representation theory point of view, but I wonder, do they have any geometric meanings?
Very nice question. And in type A case, so there are several geometric constructions of McDonald polynomials, but the related algebra is different from affine algebras. Which I have mentioned this quantum toroidal GL1 was a neon-band algebra. This algebra has some geometric realization, geometric meaning.
Okay.
And using that, we can reconstruct McDonald polynomials or functions in terms of that geometrically realized algebra.
This one might looks like have something to do with conformal field theory. Looks to me.
Yeah, so it is a kind of deformed shape. Yeah.
Okay.
Yes, I can make a comment. In the in the construction of not invariant, the McDonald polynomial on the representation theory DAHA plays an important role. So that is some application to topology or geometry.
Yeah.
Right?
Yeah.
Yes. So non-invariant meaning, so non-symmetric McDonald. Yes, this one is related to the so-called Daha link polynomial relaxation. Related to some topological invariant of knots or links. There are many recent studies on the topics, which may appear in private talk. Sorry. So in that context, the affine Hecke algebra appears in some physical context. Sorry. I didn't know that. Thank you, Kano-sensei.
Maybe another, I don't know whether it's a common or not, but I just wonder, if I remember correctly, I sort of heard of this or read Jules' paper about conformal field theory or VOA during my graduate school years. I remember one of his motivations to understand the McDonald polynomial.
Yes.
So yeah, so there also have some connections.
Yes. So,
but I wonder. So I mean that's kind of an old story. But for the later on, you have this all this double Hecke algebras coming out of this from not only from this place, maybe from many other places as well. So I don't know why they're so ubiquitous. I mean, it have been appeared in so many places. So I just don't understand why. There must
why?
Reason for all this like double Hecke algebras to appear. What's the fundamental? I mean, is there any philosophy behind this?
Yeah, I agree your comment and your philosophy. Yeah, I don't know a good answer to your question.
Okay.
Yeah. And actually, that question is one of my thing of study.
I see. Yeah.
A very good question, I think.
That is because mysterious.
I'm sorry. Actually, that question also applies to VOA, right?
Yeah.
Why VOA appears so many places or ubiquitous?
Well, I remember this type of question have been appeared in many different talks and the conference and the people. I remember Michael Douglas was once a physicist. He's a physicist. He said once he said, okay, maybe everything is related to everything else. Maybe this is the main feature of the mathematics and the physics in the modern age, because within quantum field theory framework, it looks like everything is connected to everything else. But that's an empty statement. I mean, you cannot make it a deeper understanding of this. But maybe it's not entirely empty. I mean, I'm not sure. Might not be entirely empty. It looks like something is unifying mathematics. Yeah, maybe it's quantum field theory. Maybe some infinite dimensional structures. I don't know. Yeah, it was really nice. So, any other questions? Oh, I didn't control the time very well. I'm sorry. So it's already almost time for the next talk. So let's thank the speaker again. Thank you.
Thank you very much.
Yeah, in 1 minute we'll start the next talk, but I will pass the chair to you. So yeah.
Yes. So let us restart at I posted a message. So let us restart at 3:45 in China time in 5 minutes. Is it okay, Hayashi Sensei?
5 minutes? I don't see. So
45.
next, now.
Not now. In 5 minutes.
In 5 minutes.
Now it is 40.
Now 40, yes. So the next speaker will start 40.
Yeah, but let us take some break here.
You want to take a break? Okay.
Yes. Sorry.
Okay.
はい。
慎太郎、いやね。
So can you see my slide?
Yeah, it is okay.
Yes.
Yeah. So now let us restart, and the final speaker of today's session is Dr. Ji-Hao Zhang from USTC and SUSTech. The title is Enriched Categories and Their Centers. So please start.
Okay, thanks. And I would also like to thank the organizers of this workshop. Okay, in today's talk, we have seen the applications of the enriched category theory in physics, especially in Rongge Xu and Oliver Young's talk, and also in Liang Kong's talk. And in my talk, I will give an introduction of the mathematical theory. This talk is based on a joint work with Liang Kong, Wei Yuan, and Hao Zheng. Okay, so first we just briefly recall the definition of an enriched category. Enriched categories can be viewed as generalizations of ordinary categories, but to define an enriched category, we need to first fix a monoidal category, and this monoidal category is called the background category. Also, we have some objects, and for every two objects, there is an Hom space. This Hom space is not a set, but an object in this fixed background category. And there are some composition morphisms and identity morphisms, which are one morphisms in this background category. And like an ordinary category, the composition is associative and unital. So the first example, an ordinary category is a set enriched category. Here, set means the monoidal category of sets. And another example, as in today's talk, we have seen given a 1D quantum liquid phase, which may be gapped or gapless, and with or without symmetries, the observables in the long wavelength limit form an enriched category. And indeed, they form an enriched fusion category. This enriched category is called the topological skeleton of this phase. Another important class of examples are given by the so-called canonical construction. And let me explain this construction. First, we need a monoidal category B and a left B module M. And for every object X in M, there is an action of B on X, and this is a functor from B to M. If the right adjoint of this functor exists, we see that M is enriched in B. And the object XY, which is the right adjoint acting on Y, is called the internal Hom of X and Y. And from this adjunction, we have the following results. First, we have a morphism from the tensor unit in B to the internal Hom XX. This morphism is induced by the identity morphism on X. And also we have a composition morphism induced as a following equation. And in the first step and the last step, the morphism internal XY tensor X to Y is induced by the identity morphism on the internal Hom XY. So we have seen that there is an enriched category BM. The background category of BM is just B, and the underlying category, we have not defined the underlying category. And the objects of this BM is just the same as M. And the Hom spaces are given by the internal Hom. Also, the composition and the identity morphisms are given by the above construction. So this is a canonical construction. Another way to construct enriched categories is given by the operation called changing of the background category. First, we recall a Lex monoidal functor is just a functor equipped with two natural transformations. And these two natural transformations should satisfy the Euler conditions of a monoidal functor. But the difference is for monoidal functor, these two natural transformations must be natural isomorphisms. For Lex monoidal functor, they are not necessarily invertible. So if there is an A enriched category AL, and the Lax monoidal functor from A to B, then this Lax monoidal functor induces a B enriched category, whose objects are the same as AL, but the Hom spaces are mapped by this Lax monoidal functor. And as a special case, we consider that B is just the category of sets, and F is a Hom category from the tensor unit. Then the changing of the background category just gives an ordinary category. And this category is called the underlying category of AL. And as you can see, if we have a canonical construction BM, its underlying category is just the category M. Okay, so this is a changing of the background category. And let me remark that for an enriched category, changing of the background can be viewed as a functor. So we can have a new definition of an enriched functors. So let me give the definition. An enriched functor between two enriched categories is defined by the following data. First, we need a Lax monoidal functor between two background categories. And this functor is called the background changing functor. And we have a map between the objects. And for every two objects, we have a map between the Hom spaces. But the Hom space in A should be mapped by this background changing functor. And also, like an ordinary functor, the enriched functor should also preserve the composition and identity morphisms. As a special case, if B is the same as A and the background changing functor is just the identity functor, such an enriched functor is called an A functor. And this is a traditional definition of an enriched functor. For example, you can find this definition in Kelly's famous book on enriched category theory. So what we do is to find a new definition of enriched functors where these two enriched categories can have different background categories. I would also like to remark that every enriched functor can be decomposed as the composition of two enriched functors, where the first enriched functor is just only changes the background, and the second functor is a B functor. Also, for every enriched functor, we can define its underlying functor between two underlying categories. And it is defined by the following map. And similarly, we can define the notion of an enriched natural transformation. It is also defined by a background changing natural transformation and an underlying natural transformation. And the background changing natural transformation should be monoidal. Okay, so all enriched categories, enriched functors, and enriched natural transformations should form a two category. And we denote the two category by this notation, Lax ECAT. It is also a symmetric monoidal category with the monoidal product given by the Cartesian product. And in practice, we also consider a sub-two category in which we only consider the enriched functors whose background changing functors are strongly monoidal, not Lax monoidal. And this sub-two category is denoted by ECAT. If we fix a monoidal category A, then there is a two category of A enriched categories, A functors, and A natural transformations. This is a traditional definition of a two category enriched categories. And you can also find this definition in Kelly's famous book. So what we do is to find a new two category in which the enriched categories can have different backgrounds, not a fixed one. Also, in this new two category, we can define the notion of enriched monoidal categories, enriched brilliant monoidal categories, and enriched symmetric monoidal categories as certain EN algebras in this symmetric monoidal category ECAT. But in my talk, I will not give you the precise definition of EN algebras. I just want to provide some intuitions. We can imagine an EN algebra as a collection of some particles living in an n-dimensional space. So these particles can be fused together in n directions. So you can define an EN algebra as an object equipped with incompatible multiplications. Here, the compatibility means every multiplication is a homomorphism between is a homomorphism with respect to other multiplications. In particular, an E0 algebra is just an object equipped with a morphism from the tensor unit to X. Okay. For example, in the category of vector spaces, we can define EN algebras, and an E1 algebra is just a vector space equipped with only one multiplication, so it is an ordinary algebra. And for E2 algebra, it is a commutative algebra. Why? Because an E2 algebra is just a vector space equipped with two multiplications. And graphically, I just draw these two multiplications as horizontal multiplication and vertical multiplication. So what is the compatibility condition of these two multiplications? If we consider 4 elements, well, you can imagine that there are 4 particles in this space. So you can multiply them in 2 different ways. You can first multiply them horizontally and then vertically, or first vertically multiply them and horizontally multiply them. And the compatibility means these 2 ways of multiplication should be the same. So we have the following equation. And from this equation, you can see that the horizontal multiplication is the same as the vertical multiplication, and both of them are commutative. This is a classical argument of why the higher homotopy groups are commutative. Also, we consider the category of all categories. And in these 2 categories, an E1 algebra is just a monoidal category, and E2 algebra is a brilliant monoidal category. The argument is basically the same as above, but these 2 equations, well, these 4 equations should be replaced by natural isomorphisms because there are non-trivial 2 morphisms in the 2 categories of CAD. And for E3 algebra and higher EN algebras, they are just symmetric monoidal categories. Okay, so in the symmetric monoidal 2 category ECAD, we just define the EN algebras as enriched monoidal category, enriched brilliant monoidal category, and enriched symmetric monoidal category. We can take in their underlying category, and you can find this operation is a symmetric monoidal 2 functor. So it maps an EN algebra to an EN algebra. And similarly, you can take in the background category. This is also a symmetric monoidal 2 functor. So if we have an enriched monoidal category, it is an E1 algebra in ECAD, then the underlying category is a E1 algebra in CAD, which is a monoidal category. And the background category is a E1 algebra in the category of E1 algebras in CAD, which is just a brilliant monoidal category. And for enriched brilliant monoidal category, it's an E2 algebra. So both the underlying category and the background categories are E2 algebras. So the underlying category is brilliant monoidal, but the background category is symmetric monoidal. And for enriched symmetric monoidal category, its underlying category and the background categories are both symmetric. And conversely, we can consider the canonical construction. The canonical construction can be extended to a symmetric monoidal 2 functor from 2 category to ECAD. I will not tell you the detail of these 2 category, but I just tell you some results. First, we recall the canonical construction just maps a monoidal category and the left module to an enriched category. And for E1 algebras, we can consider the so-called monoidal left module. What is a monoidal left module? We first need a brilliant monoidal category. And the monoidal module over a brilliant monoidal category C just means a monoidal category M equivalent with a brilliant monoidal functor to the Drinfeld center of M. And the canonical construction just maps this monoidal module to enrich the monoidal category. And similarly, you can define the notion of a brilliant left module. If we have a symmetric monoidal category, a brilliant left module over this symmetric monoidal category is just a brilliant monoidal category M equivalent with a symmetric monoidal functor to the Milgauss center of M. And the canonical construction maps such a brilliant left module to enrich the monoidal category. And if M itself is symmetric, then the canonical construction is enrich the symmetric monoidal. In every symmetric monoidal category, you can define the EN center of an EN algebra by some universal properties. And the EN center is, by definition, it is an EN+1 algebra. I will not tell you the definition of what is the EN center, but I give you some examples so you can have the feeling of the center. First, we consider a category VEC of vector spaces. Then the center of a vector space is given by the endomorphism algebra. And the U1 center of an U1 algebra is just the Euler center ZA, where ZA is just the subalgebra consists of elements that commute with all elements in A. And in the two-category cat, the center of a category is the endofunctor category. And the E1 center is the so-called Drinfeld center. The E2 center is the so-called Milgauss center. And we can also compute the centers of EN algebras in the two-category ECAT. So we just leave the results of enriched monoidal categories obtained from the canonical construction. First, we consider the case that B is a rigid monoidal category and M is a B module. Then the canonical construction gives an enriched category Bm, and we can compute its center. Its center is an enriched monoidal category. The background category is the Drinfeld center of B, and the underlying category is the functor category of B module functor category to from M to M. And similarly, if we have a brilliant monoidal category and the monoidal left module, its canonical construction gives an enriched monoidal category Cm. And you can compute its E1 center, which is an E2 algebra. Enriched brilliant monoidal category. Its background category is a Milgauss center of C, and the underlying category is just a Milgauss centralizer. And for enriched brilliant monoidal category, you can compute its E2 center. The background category of enriched brilliant monoidal category AL is the same as A, but the underlying category is the Milgauss center of L. As a special case, we get our main results. If A is an indecomposable multifusion category and L is a finite semi-simple left A module, then the canonical construction gives an enriched category AL. You can compute its center, which is an enriched fusion category. And this enriched fusion category can also compute its U1 center. And we get a result is VEC, which is trivial in some sense. So this result means the U1 center of the center of this enriched category is trivial. And let me tell you the physical meaning of these results. For this enriched fusion category, we can imagine that it is a topological skeleton of a 1+1D quantum liquid phase. And this enriched category AL, it is a category of boundary conditions of this 1+1D quantum liquid phase. So the boundary bulk relation just says the bulk is a center of the boundary. So the center of this boundary categories just get the bulk enriched fusion category. And this U1 center of this enriched fusion category describes the 2D bulk of this 1 plus 1D quantum phase. So this result means the 2D bulk of this 1D phase is trivial. So physically, this result says the bulk of a bulk is trivial. And in one-dimensional higher, there is a similar story. We consider a non-degenerate Brillouin fusion category C and an indecomposable multifusion left module defined by a Brillouin tensor functor. Then the canonical construction CM just it is a enriched fusion category. And this enriched fusion category is a topological skeleton of a 1 plus 1D quantum liquid phase. We can compute this U1 center, which describes the 2D bulk of this phase. And we can also compute the E2 center of this enriched symmetric, enriched Brillouin category. And the result just describes the 3D bulk of the 2D bulk. And we again get the bulk of a bulk is trivial result. And mathematically, the result is the center of the center is trivial. Physically, it means the bulk of a bulk is trivial. Okay, so that's my talk. Thanks for listening.
Thank you for the interesting talk. And is there any comments or questions?
Hi, can you hear me?
Yes.
Okay. I get a question. Can you be more precise about the symmetric monoidal two-functor from something like modules, monoidal categories and modules to ECAT? I think you do not intend to elaborate on this, but I'm curious what this category, this page, what this symmetric monoidal two-functor is.
Yeah, there are two categories of monoidal categories and modules. So, well, its objects are a pair, a pair of monoidal categories and modules, just like B and M. And these two functors map such an object to an enriched category Bn.
Okay. And I have
maybe the most non-trivial thing is what is the definition of functors between two such pairs? I mean, the one morphisms in these two categories is really non-trivial.
Oh, okay, I see. So what is this one morphism?
Well, the detail is a little hard to explain, but it is also a pair from. It is also a pair between two such pairs.
Okay.
Yes.
Okay. Then my question is, can I compute center directly in this domain 2 category?
Yes, but we have not computed these results. These two functors is not in two equivalents, so we believe the center in these two categories is not the same as the center in the two category ECAT.
Okay.
And also in these two categories, the EN algebras are not the same as the one introduced below, because a monoidal left module is just an example of U1 algebras in these two categories. And in general, there are some other wild examples. Yes.
Oh, okay. Interesting. Thank you.
Is there any other comments?
Can I also ask a question? Actually, I'm curious about your explanation to the last question. Can you briefly explain why the two category of monoidal categories and modules, they are different from your ECAT? Because it seems the canonical construction does not really lose any information, right?
Yes.
So what kind of wild phenomena is happening in the domain that prevent you from getting the same center?
Well, well, I just explained two reasons. The first reason is that the canonical construct is not surjective. I mean, there are some enriched categories in ECAD which are not, which cannot be obtained from the canonical construction. And the second one, I want to see, for example, an E1 algebra in these two categories may not be a monoidal left module. For example, if M is a monoidal category, but this functor is just really the Lex monoidal functor. And you can also do a canonical construction to get a.
But your ECAD is not, the morphisms of background category is not Lex, right?
Yes, but you can still get an object.
Sorry, I mean, in your domain category, is one morphism Lex between underlying monoidal categories to be Lex, or some kind of assumptions you are making here?
Well, there are also two definitions of the domain category, but if we choose ECAD here, the domain category should be, the one morphism should be monoidal and not Lex monoidal. But this is an object, not a one morphism.
So you are saying if you consider E1 algebra object in that two category, it would, this is, so the phi here could potentially be Lex. Is that a claim?
Well, I know, I get your point. Well, no, if the two category, in these two categories, if the morphisms are monoidal, then the only possibility is that this is a brilliant monoidal font. I think there's no other possibility. Well, but in fact, we do not consider such a restrictive two category. In our paper, the canonical construction is from the two category to Lex ECAD. Yes.
Okay, so yeah, because my intuition kind of tells me your target category should be kind of the generalization of your domain category, yes. But it's kind of preserving structure kind of generalization. So you shouldn't really obtain a different result with few compute centers.
Yes.
Yeah. That's kind of a comment. Yeah.
Xu Hao, is your intuition wrong? Is your conclusion is that your intuition is wrong for this symmetric monoidal two functor, or right?
I'm not sure. So if you insist your domain and target categories, the morphisms between monoidal functors to be strong, I think we should agree that my intuition is kind of right. But if you consider Lex one, I don't know. I haven't computed impulse. So yeah. And also in your definition about ECAD, your natural transformation between Lex monoidal functors, they are not Lex version, right? They are kind of strong.
Well, there's no Lex version of monoidal natural transformation. I mean there's no Lex monoidal transformation.
Two cells to be not necessarily invertible.
Well, enriched natural transformations are, by definition, not necessarily invertible.
I see. Yeah. I seem to confuse something. Yeah, that only happens in higher categorical case where
yes,
cells you can.
Yes, for one category, then the monoidal natural transformations are no lax versions.
Exactly. Yeah.
Is it okay?
Yes.
Yeah, any other questions or comment? Then let us thank the speaker again. And this is the end of today's session. Hayashi Sensei,